Let's imagine that for some reason you want to make your house out of copper. I don't know why you want to do that, but let's just say you do. Let's imagine you've got one wall of your house that's 10 meters long and 3 meters high, and let's imagine you're going to make these copper walls 1 centimeter thick. Now, on a cold day in winter, the outside temperature, let's say, is 4 degrees centigrade, while the inside you want to keep at 20 degrees centigrade. Now, let's imagine that actually the inside wall and the outside wall are those temperatures. There's actually going to be some differences in those, even in a situation like this. There's going to be some air on both sides, but let's just, for the sake of argument, imagine that the inside temperature of the wall is 20 degrees, the outside temperature of the wall 4 degrees. Let's figure out how much energy would lose through this wall, would escape from your house in 1 hour. So in a time of 1.00 hours, Q is equal to, well, K, the thermal conductivity for copper is 390 joules per second meter degree Celsius, times A. Now what's A? Remember, A is the area that's separating the two temperatures. In that case, it would be this area of the wall, which would be 10 meters by 3 meters, 30 meters squared, times delta T. Now we've got 20 degrees on one side, 4 degrees on the other. That's a temperature difference of 20 minus 4, 16 degrees Celsius. Times little t, the time, well, for 1 hour, we need to put this in the standard SI unit of seconds, so 3,600 seconds. Divided by L. Now remember, L is the distance between the two temperatures. The difference between the two temperatures would correspond to the thickness of the wall, 1 centimeter. In other words, 0.0100 meters. Now, we multiply this out, and what do we get? We find that Q is equal to 6.7 times 10 to the 10th joules. Now, if this were actually going to be something that might show up on a electrical power bill or something like that, electricity bills are usually listed in a different unit of energy called a kilowatt hour. Now, what is a kilowatt hour? 1 kilowatt hour, well, that is a kilowatt. A kilowatt is 1,000 watts, and a watt is a joule per second. Times an hour, or 3,600 seconds, the seconds cancel, multiply this out, and what do we get? We get 3.6 times 10 to the 6th joules. So a kilowatt hour is 3.6 times 10 to the 6 joules. In other words, 3.6 million joules, or 3.6 megajoules. So we can convert this, dividing by 3.6 times 10 to the 6 joules and multiplying by 1 kilowatt hour. This turns out to be 1.9 times 10 to the 4th kilowatt hours. Now, I'm not sure exactly how much a kilowatt hour costs right now, but the last time I looked on my electricity bill, it was 15 cents per kilowatt hour. Which means that your 1.9 times 10 to the 4th kilowatt hours would cost about $2,800 an hour. So you would have a heating bill in the winter of $2,800, or almost $3,000 an hour. I think you might want to rethink your idea of making your house out of copper, or at least get some insulation on those walls. All right, very, very good. Now, what about the last method of heat transfer? Our last method of heat transfer is radiation. Radiation is the process in which energy is transferred by means of electromagnetic waves. Now, earlier when we were talking about the convection currents in the Earth's atmosphere, we talked about how energy from the sun came and struck the Earth's atmosphere to heat it up. Now, how is that energy getting from the sun to the Earth? There is no material in between the Earth and the sun, or at least a very, very small amount. So it's not conduction or convection. How is it getting here? It's getting here by the sunlight. And sunlight is one form of electromagnetic wave. So by visible light, that's one method that energy can get from one place to another. But there are other kinds of electromagnetic waves that are not visible. In other words, that we cannot see. For example, there's infrared, ultraviolet, radio waves, that kind of thing. Often when we think of heat, if you feel heat coming off of something, if it's not a convection current, that heat is typically infrared radiation. That is another kind of electromagnetic radiation that has a wavelength that's outside of our range of visibility. It's longer than red light, too long for us to actually see with the naked eye. Now, what kind of energies are we talking about when we're talking about these different kinds of electromagnetic radiation? Do they all have the same kind of energy, or what? And how do things actually heat up by absorbing this electromagnetic radiation? So, why do things look the way they do in terms of the colors? Why, for example, does this red square look red? Well, the light from our light sources, which is basically white light, strikes that red square. That square absorbs, basically because of the ink on it, it absorbs all of the colors except that red, which it reflects. So when we look at that square, we have the red light coming into our eye, and so it looks to us red. Now, why is this green? Because the light striking that is absorbed by, it absorbs all of the colors except green and reflects green. So when we see it, it looks green. This square absorbs all of the colors except blue and reflects blue. So we see that as blue. Now, this area here looks white because it reflects all of the colors that land on it. And when all of the colors in terms of light are mixed together, we perceive all of those colors of light as white. This one looks black because it absorbs all of the colors. All of the colors that land on that are absorbed, and so very, very little is reflected, so when we look at it, it looks black. Now, there's a very particular, very important kind of object that absorbs not only just the visible light that lands on it, but all radiation that lands on it. An object that absorbs all radiation, visible light, infrared, radio waves, ultraviolet, X-rays, everything. That is called a black body. You can imagine if you were to look at it, it would be completely black, absolutely perfectly black. That would be a black body, something that absorbed all light that lands on it. But that doesn't mean that no light comes from a black body. A black body does emit light. It doesn't reflect it, though. But it emits light because of its temperature. It emits light anytime it's above 0 Kelvin, absolute zero, which is basically any physical object. It will emit what's called a blackbody spectrum. So a perfect black body, which is a perfect absorber, will also emit light, and the form of that light, the amount of light in different, the energies at different wavelengths, is called the blackbody spectrum. Now let's take a look at that just for a minute. Let's imagine we've got this black body here. How much energy is that thing actually emitting? Well, the larger it is, the more energy it would emit. So it's actually proportional to its surface area. It's proportional to A, where A is this external surface area. Also, as usual, how much time do we give it? In 1 second it would emit a certain amount of energy, in 2 seconds it would emit twice as much. So the amount of energy is actually proportional to time. Now, the hotter the object, the more energy it emits. Now, we might guess that it's proportional to the temperature, but actually it's not. It's proportional to the temperature to the 4th power. Now, there's something very, very important about this temperature here. Up until this point, any temperatures that we've always dealt with have always been a delta T, a change or a difference in temperature. The difference in temperatures between two objects. Like with the conduction equation, we had the difference in temperature between the hot end and the cold end. In this equation, we're actually using the temperature of the object. So, do we want the temperature in Fahrenheit and Celsius? We want the temperature in Kelvin. This has to be in Kelvin. Now, how do we find the temperature in Kelvin? Well, the temperature in Kelvin is related to the temperature in Celsius, but shifted by about 273 degrees. 0 degrees Celsius is equal to 3 sig figs, 273 degrees Kelvin. 100 degrees Celsius is 373 degrees Kelvin. So a change of 1 degree Celsius is the same as a change of 1 Kelvin. In other words, if 0 degrees Celsius is 273 Kelvin, 1 degree Celsius is 274 Kelvin. 2 degrees Celsius, 275 Kelvin. So if you increase the temperature of 1 degree Celsius, you increase the temperature of 1 Kelvin. We can write a conversion here in that the temperature in degrees Celsius is equal to the temperature in Kelvin minus 273. So you just take whatever the temperature is in Kelvin, subtract 273, and you get the temperature in Celsius. If you want the temperature in Kelvin, you take the temperature in Celsius, you add 273, and that will give you the temperature in Kelvin. So the temperature in Kelvin is equal to the temperature in degrees Celsius plus 273. Okay, in this equation, we must put the temperature in Kelvin. Okay, great. And then it's the temperature to the fourth. Now, there's another thing we need to put in here. What if this is not a perfect black body? Anything that we deal with in ordinary everyday life is not going to be a perfect black body. So there's another term we put in here called E. E is the emissivity. And it tells us how close to being a black body our object is. If E is equal to 0, it is not an emitter at all. It's as far away from a black body as you can get. That would be something like a perfect reflector, something that doesn't emit light because of its own temperature, but only reflects light off of it. E equals 1, that would be a perfect black body. So E equals 1 means a perfect black body. Great. And then we can actually make this an equality if we just stick in a constant of proportionality. So I'm going to write that out, and then we'll actually stick some numbers in. Q then equals E, the emissivity, times, and here I've put the constant to make this an equality, as sigma. Sigma is called the Stefan-Boltzmann Constant, and it has a value of 5.67 times 10 to the minus 8th. And you can move these things around and see that the units would then be joules per second, meter squared, Kelvin to the fourth. And then times T to the fourth, times A, the area, times little t, the time. So let's figure out how much energy does a person radiate. So a person has a temperature. How much does a person radiate? And let's say in 1 second. Well, what we have is Q is equal to E, the emissivity. Now, actually, people have different emissivities depending on their skin tone. So let's pick someone right in the middle, say a nice gray person with an emissivity of 0.5 times sigma, 5.67 times 10 to the minus 8th joules per second, meter squared, Kelvin to the fourth, times T. Now, what's T? T would be a person's skin temperature. Now, that turns out to be around 33 degrees centigrade. So, do we put in 33 here? No, we've got to convert it to Kelvin. So we add 273, and that is 306 Kelvin. So times 306 Kelvin to the fourth, times A. So A, that would be a person's surface area. In other words, skin area. So what's the average person's skin area? Well, depending on how large someone is, a baby has a smaller area, a large person has a larger area. We have an average area of about 2 square meters. So I'll say about 2 meters squared times little t, and we're looking in 1 second. There we go. So we'll multiply this out, and what do we find? Well, before I put a number down, I want you to think about what you think this is going to be. Do you think we radiate a lot? Do you think we radiate a little bit? Well, the answer is 500 joules. Now, that's the energy that we are radiating in 1 second. In other words, our power is 500 joules per second. That's like a 500-watt light bulb. Actually, it's considerably more than a 500-watt light bulb because a 500-watt bulb doesn't really emit 500 watts as visible light. How is it possible that we are radiating that much energy every second? Well, keep in mind that this energy is coming out as infrared. It's not anything that we can see with the naked eye. But if you had a pair of infrared goggles and were to look at some people, they would be glowing like light bulbs. So we actually are radiating quite a bit of energy because of our temperature. Okay, well, very, very good. That's all that we have for our transfer of heat. I hope you enjoyed that. We'll see you next time.